Hello, scholars. Happy St. Patrick's Day. We talked yesterday about probability, but the big idea being that if you want to compute the theoretical probability of an outcome, it's the total number of ways to get that outcome you want divided by the total number of outcomes. So if we're flipping a coin and we hope to get heads, then the probability of us getting heads is 1, because there's only one head on a coin, divided by 2, because there are 2 possible outcomes when you flip a coin. Or if we wonder what the probability is of rolling a 5 when we roll a 6-sided die, there's 1 5 on the die, and we would divide by the 6 ways to have the outcome of rolling a die. So there's 6 different possibilities, so 1 out of 6. We're going to build up from there with the idea of a complement. Notice this is the word complement, and it's spelled with an E here. If you spell it with an I, it's something nice you might say to someone. Oh, I like your green shirt. But complement, spelled with an E, means the part that completes the whole. So if we think about it, if A is the event that it rains today, and we say, what's the probability of event A? Maybe there's a 70% chance it's going to rain today. So I would say the probability of event A is 0.70. The probability that it doesn't rain has to be whatever it is that you would add to 0.7 to get one whole, which would be 100%. So we have a name for that. That's the event of A not happening. We call that A bar or A hat. So that's just A with a line over the top of it. And we would say that the probability of it not raining, so the probability of A bar is, in this case, would be 0.3. So big idea for us, the probabilities of all the possible outcomes for an event, for an experiment, have to add up to 1. So for raining, it either rains or it doesn't rain. So those 2 probabilities have to add to 1. For the event where the experiment where we roll a die, we could get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And those probabilities, the probability of getting a 1 plus the probability of getting a 2 plus the probability of getting a 3, all have to add up to 1. So the probability, we might say, if I say event B is I roll a die and I roll a 5, the probability of event B, that's the one we talked about a second ago, is 1 out of 6. The probability that I roll a die and I don't get a 5, I would call the probability of B bar. And that's going to be whatever you have to add to 1/6 to get 1. I could write it out like this. It's like 1 minus 1/6. So the probability of B bar is 5/6. The probability that you roll a die and don't get a 5 is 5/6. So it's especially helpful in a problem like this if you look at example 3. If you roll 2 dice, and just to keep it easy to tell the different possibilities apart, let's say 1 die is red and 1 is white. So you can see here, there's 36 possible ways for those 2 dice to come out. So if I look at a question like A, what's the probability that the sum is not 6? One way to do that would be count all these combinations where the sum is not 6. That's the total number of successful outcomes. And divide by the number of outcomes, which we can count here is 36. But watch this. If I can just find the ones where the sum is 6, there's fewer of them than there are outcomes where the sum is not 6. So if I find the ones where the sum is 6, that's 1 and 5, 2 and 4, 3 and 3, 2 and 4, 1 and 5. There's 1, 2, 3, 4, 5. Am I missing any? So it's going to be faster if I say, okay, well, there are 5 ways that I could get exactly 6. So I would say the probability of rolling a 6, I spelled roll wrong. Probability that I roll a 6 is the 5 ways to roll a 6, 1 and 5, 5 and 1, 2 and 4, 4 and 2, 3 and 3, divided by the total number of possible outcomes. So the probability that I don't roll a 6, so that's roll a 6 with a bar over the top, we say the complement of, is, well, whatever I would have to add to 536 to get 1. So 5, you could subtract 1, take away 536, which is the same as 36, take away 536. It's going to be 31/36. So just notice how using the complement saved me the trouble of having to count that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 31 different ways to roll a not 6. It was faster to count up the ways to roll a 6 and then subtract that probability from 1. Similarly, if I wanted to find out what's the probability that the sum I roll is less than or equal to 9, I could count up all the possibilities, and it's especially nice because at least they're written out for me here. But if I notice that the number of ways to get something that's bigger than 9 are very limited, you could get, I've got them here. Right. You could roll a 12, or there's 2 ways to roll an 11, or 3 ways to roll a 10. Those are the only ways to get something higher than 9. So if I think about that, I'm going to call event A that I roll a greater than a 9. The probability of event A was those 1, 2, 3, 4, 5, 6 ways to do it out of 36 possibilities. So the probability of getting something less than or equal to 9, that's the complement. So I would call that the probability of A bar, and that's going to be 1 minus 636, or 36, take away 636, which makes 36, which could simplify to 5, 6. But the big idea here is, do you recognize you can save yourself so much time counting up possibilities if you find a probability that's faster and then think about the complement. So this one I think is easier to think of. It's faster to compute by using the complement. So a couple practice problems down here. I'm looking at like question 4. It says find the probability of A bar. If the probability of A is 0.45, what's the probability of A bar? All right, so big idea. The probability of something happening and the probability of it not happening have to add up to 1. So that was supposed to be an equal sign. So probability of A bar is going to be 1 minus probability of A, which is 0.55. Are you allowed to use your calculator? Absolutely. The big idea I need you to know is you could take the probability of A and subtract it away from 1, and that's going to give you the probability of not A. Here we go. The probability of A, if the probability of A were 1, that means 100%. That means A is guaranteed to happen. So what's the probability of not A happening? It's got to be 0. So just be prepared to do that with fractions or decimals. The probability of something happening added to the probability of it not happening have to add up to 1. So one more big idea for today. Experimental probability. What we were talking about before was a theoretical probability. Before you roll a die, what is the probability that when you roll it, it's going to be a 5? Well, that's 1 way to roll a 5 divided by 6 possible outcomes. It's going to be 1 out of 6. But now what if you actually roll a die a bunch of times? You're not always going to get 1/6 of the time that your roll is going to be a 5. So using the data you actually have of a bunch of experiments, what's the experimental probability? Well, it's the number of times the thing you wanted actually happened divided by the total number of times you did the experiment. So that's here. Number of successes divided by number of trials. So if I'm looking at this problem, I have a spinner. It looks like those are equally divided into 4 equally sized sections. you would expect, as long as it's a fair spinner, that the probability of spinning blue is going to be 1 out of 4. The probability of spinning green is going to be 1 out of 4. So here's what really happened when somebody spun the spinner 20 times. So can you say, what is the experimental probability of spinning red? Well, I had 20 times that I spun the spinner and 5 are red. So the experimental probability for spinning red was 5 out of 20, which does happen to equal 1/4. But the experimental probability for spinning green was 9 out of 20. So just know that even if you had an expectation going in, if you have data that says otherwise and you're asked to give the experimental probability, you need to report that ratio using the data you actually have. So they have a question here. For which color is the experimental probability of stopping on that color the same as the theoretical probability? Well, we said the theoretical probability was going to be 1/4. We did happen to already find it. That was red. The theoretical probability of spinning red is 1 out of 4, and the experimental probability was 5 out of 20, and those are equivalent. If you took out blue, though, the experimental probability was 3 out of 20, which is not equal to 1/4. So for blue, the experimental and theoretical were different. So how does that show up? So the whole reason we collect data and do experiments is because we want to try to make a conclusion. We want to try to make a prediction, a guess about something that's true, either about a population or most of the time about a population. So here's an example. I interviewed a bunch of people and asked if they have a pet. And of the ones who have pets, these are the pets they have. So the question here is, so there are 1,328 out of 2,100 and adults have at least one pet. If you meet somebody and find out that they're a pet owner, what's the probability that they have a dog? Well, we assume, at least for now, because it's the best data we have, that this data is true for pet owners that we're going to talk to. The probability that they're going to have a dog is the number of dogs out of the number of people who had a pet. So 916 out of 1,328. If I asked you what's the probability that a pet owning adult has a bird, you would say it's the 93 bird owners divided by the number of pet owners, 1,328. So your assignment for today, if it's helpful, you can kind of, in case you don't have access to your book at the moment. So from page 542, question 9. Question 11, an error analysis question. Number 15, about experimental probabilities. And number 17, about a spinner. And I have one more question that I'd like you to consider. Think to yourself, what is the theoretical probability when you flip a coin that you flip heads? Okay, now I'm going to send you to a link. I want you to watch this little clip. What is the experimental probability of flipping heads in this video clip?